In this video we're going to introduce operators. So in the most general sense, an operator is something that says do something to an object, and then as a result create a new object. So to give it a little bit more of a concrete mathematical sense than that, let's use the general mathematical way it's introduced. If we have some operator O, which is just some type of mathematical operation, and it acts on a function f of x, we will get some new function g of x as a result. So this is just the most general form for what an operator is mathematically. Now in quantum mechanics, what we're going to be concerned with are linear operators. So an operator is going to be said to be linear if it acts on a series of functions in the following way. So let's say we have some operator, and some examples of operators might include derivatives, d dx, might include multiplication, x, might include division, squaring, square rooting, any type of thing which will change a function and then produce a new function as a result. So if we have an operator and it acts on a constant times a function plus a constant times another function, etc. You can have as many as you want. In principle, this can be a sum of an infinite number of them. Then this is equal to the constant pulled out times the operator acting on that function, and then plus the operator acting on the second function, etc. as far as in as many terms as you want to go. So let's give some concrete examples here of that. So for example, if I have the operator d dx, take the derivative with respect to x, and my function here, let's say c1 is 2 and function is x squared, and my second coefficient here is 3 and my second function is just x. Now if you compute this, the result we would get here would just be 4x plus 3. So this would be the same result as taking 2 times the derivative of x squared plus 3 times the derivative of x. You can see this would also give us 2 times 2x, which is 4x plus 3. So a differential operator, a derivative, d dx, satisfies the conditions for being a linear operator. d dx is indeed a linear operator, and we will see it in quantum mechanics quite a bit in various places. Now let's contrast that to the behavior of if we have 2x squared plus 3x, which again you can write in this type of form up here. And then for our operator, we have the square root operator. So taking the square root of these functions here will give us a new function on the right. Now what will this function be equal to? Will it be equal to something which looks like this? Can we take out the constant and separate the functions into their individual parts like this? The answer is no, we cannot. If you know about the behavior of how square roots work, you can't do something like this. That will not work. And so the square root operator is not a linear operator. That will not work. Okay, so we're concerned with this because in quantum mechanics, any classical quantity, any classical property is going to be represented by a linear operator in quantum mechanics. So a linear quantum mechanical operator acting on our wave function, which we're going to get from the Schrödinger equation, which we just discussed in the previous video, that these linear quantum mechanical operators will give us classical properties. So what are some examples of these? Well, some examples might include, we have the operator p hat. Operators, as you see here, are going to be denoted by this caret on top, which we usually say p hat or o hat in this case. That's the operator for momentum, the quantity p. And then the operator x hat, operator for position. If we're talking about a one-dimensional particle, that just depends on x. And then things like t, kinetic energy, running out of space there. V is going to be potential energy. And likewise, most importantly, total energy is going to be H. And this is a very special operator called the Hamiltonian operator. And in fact, much of quantum mechanics is going to be focused on this Hamiltonian operator. And in fact, given a specific Hamiltonian, a specific operator, given a specific Hamiltonian operator, you'll get a specific result for the wave function.